Problem 3 at the end of chapter 6 says to move register indirect with pre-decrement W1 to W0 register direct, assuming these initial register and memory contents. Our solution is going to be as follows. We're going to take W1, we're going to decrement it because this is a pre-decrement operation. We're going to decrement it by 2 because this is a word operation. So W1 contains in it 806 minus 2. The new value is going to be 804. At this point, we need to do this register indirect read operation. Because this chapter is talking about C pointers, here I'm going to use the C dereferencing operator to indicate this indirect read operation. So we're going to treat W1 value as a memory address. So we're going to take the contents of memory location 804. So 804 has 80FF, and that's going to be the operand that is going to be moved into W0. So the new values of W1 is going to be 804 and W0 is going to be 80FF. Problem 5 is the same as the previous problem, except now this is a byte operation instead of a word operation. That means that for this pre-decrement register indirect addressing mode, we'll only subtract 1 because it's a byte operation. So the new value of W1 is now going to be an 805. At this point, we're going to move to W0, the byte pointed to by W1. W1 has the address 805. So 805 is going to be the most significant byte of 804, so this 80 is going to be moved to the least significant byte of W0. So this byte right here will become 80. The most significant byte of W0 will remain unchanged, so the new value of W0 will be 0880, while W1 is going to be 0805. Problem 7 says to move W2 register direct to W0 register indirect with post-increment addressing. Solution written in C pointer notation. This says to copy the value of W2 to the memory location pointed to by W0. W0 contains in it an 804, so we're going to be modifying memory location 804 by writing the contents of W2 to it. W2 has an 8301, so the new value of 804 is going to be an 8301. 8301. Here, because of this post increment, we're going to increment W0 after this memory write is done. We're going to increment it by 2 because this is a word operation. So W0 has an 804 plus 2, so the final value of W0 will be 806. Problem 9 is the same as the previous problem, except that it's a byte operation instead of a word operation. So we're going to take the least significant byte of W2 and write it to the byte location pointed to by W0, which is going to be 804. So that means that 804, this least significant byte, is going to be modified by copying the 01 to it. So this value right here is going to change to a 01. So that as a word, the final value of location 804 is going to be 8001. Because this is a byte operation, that this is post increment, we're then going to increment W0 by 1. So 804 plus 1, the final value of W0 is going to be 805. Problem 11 says to move register indirect with register offset using W1 and W4 to W2. The first step is to compute the effective address of the source operand. So that's going to be W1 plus W4. W1 contains in it 806. W4 contains in it 04. So our effective address is going to be 806 plus 4 is 80A. So W2 is going to be the contents of memory location 80A. If we take a look at 80A here, it contains a CE46. This is a word operation, so the 16-bit value CE46 will be written to W2. So the final value of W2 is CE46. Note that this addressing mode here does not affect either W1 or W4. The only register that is affected is W2. Problem 13 says to move W1 register indirect to W0 register indirect with post increment. For the solution, this means that we're going to be writing to the memory location pointed to by W0 the contents of the memory location pointed to by W1. W0 contains in it 804, so that means that location 804 is being written to. W1 contains in it 806, so that means we're taking the contents of what W1 is pointing at. So we look at memory location 806. It contains the word value 7B03. So the 7B03 is being written to location 804. So the new value of location 804 is going to be 7B03. Finally, we want to post increment W0. So W0 contains in it 804. We're going to increment by 2 because this is a word operation. So 804 plus 2 is going to be 806. Problem 1 tests your understanding of C arrays and C pointers by having you execute this code and determine the memory contents after all the code has been executed. This line right here declares an array of 2 elements of signed 16-bit values. The problem states that these values should be stored at location beginning at location 800. Since each one is 16 bits, they each take up 1 word of memory. So x of 0 is stored at location 800. 802 is going to contain the value x of 1. This line here is going to declare a pointer to a 16-bit signed integer. Recall that all pointers in PIC24 semi-language are going to occupy 1 word of memory. So this word right here, 804, is going to contain the value of this pointer variable y. So we now need to begin executing this code. This first statement here is going to assign 5 to x of 0. So that means that these contents here is going to be 005. The next one is going to assign a negative 7 to x of 1. We need to determine the hex value of this. First of all, the magnitude 7 is going to be the value 0007. We need to subtract that from 0 because this is a negative number. So during the subtraction, we're boring across 0. That becomes a F. This is 16. 16 minus 7 is going to be 9. So this final value here is going to be FFF9. So at location 802, corresponding x of 1 is going to be the value FFF9. We now know that after these 2 assignments here, memory contents is going to look like this. So now let's execute this statement here, which is going to say take pointer y and assign to it the address of x of 1. But the address of x of 1 is 802. So our new pointer of y here is going to be 802. At that point, this statement here is going to say, alright, take what y is pointing at. What is y pointing at? Y is pointing at x of 1. X of 1 contains what? X of 1 contains a minus 7. So it's going to say take a minus 7 and add to it 3. And then copy that back to whatever y is pointing at. Or y is pointing at x of 1. So the new value of x of 1 is going to be minus 7 plus 3 is going to be a minus 4. A minus 4, if we convert that to 2's complement, we'll see that that is equal to FFFC. So this new value here is going to be 0xFFFC. Also, we could have said, well, we're adding 3 to this content, so 3 plus 9 is going to be 12, which is C. That's the other way to get this value. So after execution of this statement right here, we know that x of 1 is now going to contain a negative 4, which is going to be an FFFC. We now need to do this pointer arithmetic here. We're decrementing the value of this pointer. There are 2 ways to reason about this. One way is say, okay, this guy is pointing to a 16-bit element, and it's currently pointing at x of 1. When we decrement this pointer, then we're going to point to the next element in the array, the previous element in the array, because it's a decrement. So now we're going to point to x of 0. So this guy right here is going to change to the address of x of 0, which is going to be 800. The other way to do it is to remember that when we decrement this pointer, what we're really doing is we're saying that pointer value minus the size of in bytes this data type. So we're subtracting 2 from it. So 802 minus 802 minus 2 is going to be the new address of 800. In any event, after we finish executing the code, these memory contents, x of 0 contain 5, x of 1 contain negative 4, and y will contain 800. Another way to reason about this code is simply write symbolic values here in the constants instead of hex values. So here we're going to go ahead and write 5 for this assignment here. X of 1 is going to be assigned the value -7. This value y, the pointer value y is going to be assigned the address of x of 1. So this is going to be the address of x of 1. Then at this point we're going to take what y is pointing at. Y is pointing to x of 1. So that's going to be the value -7. Add to it 3. Stick the result back to where y is pointing to x of 1. So that means that the new value of x of 1 is going to be -4 after this. And now here what we're going to do is we're going to say decrement this pointer y by 1, because y is pointing at x of 1. If we decrement it by 1, it's now going to be pointing at x of 0. So at this point we can say, all right, x of 0 is going to contain 5, x of 1 is going to contain a -4, which is going to be a 0x f f f c, and finally y is going to contain the address of x of 0, where the address of x of 0 is 800. So this hex value is going to be 800. This problem is from a sample test and is like the previous problem that we wish you to execute the C code and then give the memory contents after the C code has been executed. So let's first assign locations to these variables. A is a pointer to an 8-bit variable, so it's going to be in the first word of memory here. B is a pointer to a 16-bit variable, so it's going to be the next word of memory at 802. C is a 16-bit variable assigned, so it's going to be at 804. D is a 32-bit signed variable, so it's going to take up these two memory locations here. This would be the least significant word, 806, and 808 will be the most significant word. Finally, this is a 4-element array with each element being 8 bits. So this word 80A is going to contain the first 2 elements, and this word 80C is going to contain the next 2 array elements, 2 and 3. So let's begin executing this C code. First thing we're going to do, we're going to assign -10 to D. So these 2 words of memory will have a -10. We'll write the hex value later. Then variable C is going to be assigned the value 20. So C is going to have the value 20. Pointer A is going to be assigned to the address x of 1. So pointer A here is going to have the address of x of 1. Pointer B is going to have the address of this 16-bit variable C. So pointer B is going to have the address of variable C. Now let's examine this statement right here. We're going to take what B is pointing at and add 5 to it. But what is B pointing at? B is pointing at C. So C has the value of 20. So we're going to take 20, add 5 to that, and we'll get a value of 25. Where is this written? This is written back to where B is pointing, where B is pointing at C. So that means that C is going to change to 25. This statement right here is going to copy 64 to what A is pointing at. Well, A is pointing to x of 1. X of 1 is sitting down here, so that means that this is going to be 64. What is it x of 0? Well, if we assume that these are all global variables, and typically a C compiler will clear these to 0, so this will be 0, 0 for x of 0, and these 2 values will both be 0 as well. Now let's examine this statement. We're going to take the pointer A value and add 2 to it. There's 2 ways that we can think of this. One way is to think about what this is pointing at. Pointer A is pointing at array element x of 1, and which is an array of 8-bit values, and that's the data type that A is, 8-bit values. So if we add 2 to it, then we're going to be pointing at array element 3. So this will now contain the address of array element 3. The other way to do this is think about this as hex addresses. A did contain the address of x of 1. What's the address of x of 1? The address of x of 1 is going to be 80B. When we add 2 to it, remember this is pointer arithmetic, we're going to take this 2 and we're going to multiply it by the size of whatever this data type is, which in this case is 1. So we're simply going to be adding 2 to this value. So if we take 80B and add 2 to it, we're going to get as a hex value, we're going to get 80D. Well, what is 80D? 80D is actually, here 80A is 0, 80B is 1, 80C is x of 2, and 80D is going to be x of 3, which is the same thing that we got here. It agrees. So it's now, so pointer A is now going to be pointing at x of 3. If we want to write these as hex values, obviously a 25, if we write that in hex, is going to be a 0, 0. 1 is going to be 16. 25 minus 16 is going to be 9, so that's going to be a hex 19. This guy, negative 10. If we take the magnitude, negative 10, if we write that as a, we need to write that as a 32-bit number. It's going to be 0, 0, 0, 0, A. That's the magnitude. If we subtract that from 0 to get the 2's complement value, that's going to be A from 16 is going to be 6. We're boring across all of these zeros, so all these zeros here are going to be left as F's, which means that this upper word here is going to be F, 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 and so we have a bunch of F's here, and then that's going to be a 6 down there, so this word here will be F, F, F6. And at this point, we have this location filled in. It's going to be 80D. We have that. We're missing this. What's the address of C? The address of C is 804, so this hex value right here would be 804, sitting in this memory location.